Hello, ladies and gentlemen. Thank you for joining us today for this webinar titled Inspection for Automated Composites Manufacturing, brought to you by Composites World and sponsored by CGTech. My name is Jeff Sloan and I am the editor of Composites World magazine. Today's webinar will focus on automated laminate inspection planning, available manual inspection aids for automated composite manufacturing machines, and potential automated ply inspection techniques to eliminate the need for manual inspection. This presentation will last about 35 minutes and will be followed by 15 minutes of question and answer. If you have a question, you can type it at any time during the webinar in the question field of your GoToWebinar control panel. This webinar is being recorded and when complete will be made available to you via email from Composites World. This presentation will also be made available by CGTech via email request. The email address of our presenter will be provided at the end of the webinar. Our presenter today is Matt Rodebach, the Vericut Composites Programming and Vericut Composite Simulation Product Marketing Specialist at CGTech. Matt came to CGTech with more than 10 years of industry experience with General Electric Global Research. His experience in the field includes machine operation, machine programming, and project leadership for multiple platforms. Matt received his bachelor's degree in electrical engineering from Michigan State University, a master's degree in electrical engineering from Georgia Institute of Technology, and he expects to receive his master's in business administration from Michigan State University in 2016. Please join me in welcoming Matt Rodebach. Matt?
Thanks, Jeff. I appreciate the introduction. Good morning, good afternoon, everyone. I appreciate you guys taking time out of your day to spend the next 45 minutes to an hour with me. Without further delay, I'm going to go ahead and get started, talk about the agenda for the presentation. So taking a quick look at the agenda for the presentation, I'm going to start off by providing a quick overview of CGTech, who we are, what we do, products we offer. With this, I'm going to spend a couple of minutes talking about the products most relevant for this presentation. So our Vericut Composite Programming product, VCP, and Composite Simulation product, VCS. From there, I'll go ahead and jump into automated composites manufacturing, give a quick background of what we're going to be talking about today, which is automated fiber placement and automated tape laying, give a brief description of a couple of key terms that may come up in the presentation just to make sure everyone's on the same page. From there, move on to why we may be interested in automating inspection processes for composite manufacturing, what benefits we may see, how it could save us time, savings, and why we haven't got there yet today. From there, we're going to jump into an example of an assisted manual inspection process, taking a step between a fully manual inspection and a fully automated inspection. And from there, we'll spend a few more minutes talking about some potential automated inspection technologies. So without further delay, I'm going to go ahead and get started with some of the background on CGTech. So CGTech is a leader in NC program simulation and optimization software with its Vericut product. We're a privately held firm, self-financed, started in 1988. We have the largest group of NC machining experts in the world, and we're a global company that's headquartered in Irvine, California. So as I mentioned, we have worldwide offices with support and sales offices in 11 countries around the globe, including multiple offices in the US, United Kingdom, Germany, Italy, Japan, Singapore, Brazil, China, India, etc. Another key aspect that I want to make sure I point out is that CGTech develops all of its software in-house and maintains that software in-house. So this allows for quick turnaround in customization or changes that may be required for the software. As you can see, Vericut is used by many companies of all sizes, including most of the Fortune 500 companies. This slide is a quick snapshot of the CGTech team as of January of this year, showing there's a significant amount of support behind the products, and this is the global company as we see it. Jumping into the CGTech Vericut product solutions. So start with Vericut machine simulation, which is Vericut verification and simulation, which provides a 3D simulation of CNC machines and machining operations. Vericut verification detects errors and allows for checks such as inaccurate programming, collisions with fixtures and clamps, tool collisions, holder collisions, machine collisions. It offers the ability to improve process efficiency. And the other thing it can do is help train operators and programmers without actually taking up production time or risking a crash on the actual machine. Vericut trimming simulation package builds off of Vericut machining simulation, which allows for simulation verification of composite trimming applications. Vericut's drilling and fastening, assembly and fastening allows for simulation and verification of drilling and fastening machines. So you're able to check for whether or not holes are drilled or fasteners in the wrong position, whether you actually miss a hole or fastener, collisions, and then you can also verify for double drilled or double filled holes. The products that are more applicable to this presentation today will be the Vericut Composites, VCP, and VCS applications, which you can see in the bottom right corner. VCP, which is the Vericut Composite Programming Suite, allows for path planning and NC programming generation. So what you're able to do is read in CAD surfaces and ply boundary information, add material to fill those plies according to user-specified standards and requirements. Layup paths are then linked within the software to form a specific layup sequence, and you output NC programs for the layup machine. So whether that be ATL or AFP. The other options you can look at is providing NC programs for knife trimming of composites in VCP, also pen marking, probing sequences, and then laser projection files as well, which we'll see becomes important later on during the presentation. Vericut Composite Simulation actually is able to take these programs that we create in VCP or other machine programming solutions and simulate those on an NC machine in a virtual world. So we're able to detect collisions, verify ply stacks, so looking at ply angles, location of where that ply goes, and then process validation as well. So that was a brief overview of CGTech and what we do, some of the products we have to offer. Next, I'm going to go ahead and jump into automated composites manufacturing, specifically looking at automated fiber placement and automated tape laying. So for the purpose of this talk, we're going to define automated composite manufacturing, again, specifically AFP and ATL, as a near net shape additive manufacturing process to build parts onto a mold using a CNC machine. And unlike typical additive manufacturing process, 3D printers and that sort of thing, we're not using a plastic or a metallic powder to actually build this up. We're using fiber reinforced material, typically carbon fiber reinforced, but it could be glass as well, to build those parts onto the mold. So before we get into actually getting into details on automated fiber placement, automated tape laying, I thought it would be useful to go over some key terms that may come up just to make sure everyone's on the same page. The first one that we're going to talk about is a toe or tape. And a toe we can define as a continuous strip of material. It could be carbon fiber reinforced. I also talked about glass fiber, which is typically wound on a spool. Materials can be called slit tape because it's manufactured by a slitting machine. So you start with a wide roll, it's slit down to the width that you actually need it. Typically that's 1/8 inch, 1/4 inch, 1/2 inch. And for VCP, it's essentially one pass of one single strip of material that's laid up in a part. A course then consists of all of those toes or tape within one head path of the machine. So in VCP, which you can actually see in this picture here, the yellow and blue and yellow again, each represents individual courses. So in this group here, there's actually 3 courses in this individual ply. A ply, which we can see in the diagram here, there are 3 of them pointed out, is an area of composite material laid on a form which is defined by a closed boundary. So here we have the 3. One thing to note is that these boundaries shouldn't intersect or overlap. And then a sequence would be defined as a group of plies at the same depth within the laminate of the part. So you could have one sequence be 3 plies or one sequence be 1 ply, as long as it's at the same depth of the laminate as we're laying it up. And finally, the part is the group of those sequences that get you to that near net shape final solution that you were looking at when you were designing and programming the part. So looking at automated fiber placement, what is it? Well, automated fiber placement, as we talked about, is an automated composites manufacturing process in which either individual or groups, you could have 1 up to typically 16 or 32 strips of pre-impregnated unidirectional tape, which can be steered or placed onto a mold. And as we mentioned, this is an additive manufacturing process, so you can lay up layer by layer until you actually get that final shape. Some of the advantages of fiber placement is that you're able to get a near net shape with minimal waste. So what we mean by that is we're actually able to lay material where we want to lay material and not lay material where we don't want to lay material. So when we looked at that previous slide and we saw those individual ply boundaries, each of those areas we can set up the machine to program to lay material there and not in others. But one thing you have to be careful about are some of the challenges. So you do have a minimum toe length. So it's essentially, you can't lay a 1/4 inch strip of material. You are bounded by that. So I will make that little comment as we're talking about near net shape. I have seen scrap on an overall part less than 1%. So with material costs being significant, that's a huge advantage. Another advantage is repeatability. So when we talk about repeatability, really looking at weight variation. So because you're laying this up in a controlled manner with the similar program on a similar tool, seeing weight variations as little as 0.5% after cure and after trim. And then we talked about a little bit in the past already, but material and geometry, so you're able to lay material in desired both locations and orientations. So the nice thing about orientation there is you're not limited by a given pattern or a given set of material. You can actually define what you're laying in what area. So if you want to lay a 15-degree course somewhere, or a 17-degree course, or an 18-degree course, you have the flexibility to do that. And then again, you're able to lay up steered toes on contoured surfaces. So many of the complex parts you're going to actually run into laying onto a contoured surface, and you have the flexibility to actually lay up on that without too much trouble. Some of the challenges or limitations you have to think about when you're looking at AFP would be machine investment. So the cost of these machines can be pretty significant, so you have to make sure it's going to be right for your part or suite of parts that you're looking at. You also have to take into consideration the actual machine travel. So not every machine is going to be optimized for every part you may have to lay up. So you want to make sure that you're trying to optimize to the best of your ability for each of those machines. And then internal ply shapes, I did mention this because with fiber placement you typically have 90-degree, we call them butt cuts, so perpendicular to your fiber direction or fiber orientation. So if you're trying to end a ply in the middle of a part, you're not typically going to be able to have each of those cuts follow that internal ply shape. So you may have some portion of the toe or tape extending past the ply boundary and some, not quite making it to that. And then, another thing you might want to take a look at is material cost and selection. So not every material that you can have in place is going to be readily available for fiber placement or, for that matter, tape laying. So moving on to automated tape layup, or ATL. Again, similar to AFP in that, it's a, call it near net shape manufacturing automated composite process. But instead of laying narrow strips of material, you're typically laying much wider tapes. So, a lot of times between 3 and 12 inches, and you could have multi-tapes that you're laying up as well. So, you may have 4 6-inch wide tapes that you're laying up with a single machine to obtain that structure as well. Some of the key differences between fiber placement and ATL, though, is that ATL allows for contour cuts. So instead of making those 90-degree butt cuts that we talked about, you can actually follow the contour of a ply boundary a bit better. But what that does is, typically your cutting you either perform before layup or you're slowing down significantly to perform those cuts during layup. A lot of times ATL, because you're using this wider tape, you do have the limitation that you're not able to lay up over contoured parts very well or highly contoured parts very well, and you're not able to steer the material. You end up getting wrinkling or buckling associated with that. So a lot of times ATL is used for charge layups, flat charges, and you may cut out a desired shape out of the flat charge, post form it, or keep it in the flat condition as it is. Some of the advantages, though, material laydown rates. So that could be just because you're laying wider tape. The other thing that it allows for is there's typically less opportunity for we'll call it failure. So if you're laying an 1/8-inch fiber placed toe, you have typically 16 or 32 cutters and feeds modules that could end up having issues. Here with the tape layer, you have typically 1, maybe 2, 3, or 4, so it's less maintenance as well associated with that. The other big one is material costs. So you're not slitting this material down as far from the wide band of material, so you do save on material costs as well. We did talk about one of the challenges, which is your geometry limited based on the material width. The other one is scrap rates can be very high. It could be upwards of 30 to 40%. So it's something to keep in mind as you're doing a comparison. So I do apologize. I actually had a video for this slide, and what I was trying to show was actually the layup of a cryogenic tank at NASA. So it was an automated layup process using fiber placement, and what it was showing was that the layup was completely automated, but near the end of the video it showed the inspection that was being done, and it it had the operator inspector performing that manual operation of inspection. So taking a look at each of the plies and determining whether it conforms or does not conform with the requirements of that ply. So with that, we talked about CGTech overview, automated composites manufacturing, and we're going to jump into why automated inspection, or why start looking at automated inspection. And the question is, okay, so we've done this in the past. We lay up with these machines and we do the inspection. Why change now? Why not continue with this? And we're going to take a look at a couple of different things that may help us lead to why we're going to want to look to this in the future. We'll start looking at the overall trends of the market for composite manufacturing and automated composites manufacturing, then take a look at a couple of case studies that have been presented in the past, and then follow that up with some benefits to that. So looking at the aerospace composites market, and this was completed by Composite Forecasting Consulting. Taking a look at the trends over the last 10 years or so, we're actually able to see that the composite market has been growing at about 10% year-over-year rate, and is expected to do so continuing through 2020. And if we actually look at the automated market, we're able to see that the growth rate is even higher. It's continued at a rate of about 17% and expected to continue at that rate through 2020. We're expected to have a total market of about $6 billion in material being laid up with automated manufacturing techniques. And expanding on that a little bit further, if we take a look at the manufacturing methods, in 2005, we see between automated tape layup and automated fiber placement, you had about maybe 15% of the total market being laid up with these techniques. But looking out to 2020, you can see that approximately 50% of the market is expected to be laid up with either AFP or ATL. So there's a significant growth over the next 5 years that we're expected to see in these markets. But again, just because there's growth, why do we care about inspection? And for that, we're going to look at a couple of case studies that have been presented, 2 independent case studies. The first is actually completed by Boeing and Phoebs, or MAG at the time, and this was actually on a 787 fuselage section. And over the years, there's been significant development and improvement on this process. But one thing you'll see is that at the end of the case, inspection and rework still accounted for about 63% of the total manufacturing time of this part. Actually, 47% was estimated to be the actual inspection time. With that being said, there was only 25%, or about a quarter of the time of the actual manufacturing process, that was used to lay up the part. So when we take a look at these machines, and we talked about the investment going into them, you'd like to see that you're laying up the part, nearly 100% of the time. Realistically, it's not going to be 100% of the time, but you'd like to see 70, 80% of the time you're actually manufacturing that you're laying material on your part. Looking at another case study, again, this was another 787 fuselage section, this time with electroimpact. And although it's not quite as much time, you see that inspection repair still accounts for about a third of the actual manufacturing time. And the key thing to note here is that still you're only laying up with the machine about a quarter of that actual manufacturing time. So there's significant improvement that can be done to increase your production rates, get better utilization of the machine, and hopefully save some money in the end as well. So again, you're not going to completely eliminate all of your inspection time or your repair time, but if you can cut that in half, or cut that down by 40, 50, 60%, you're looking at saving or adding 15% to 30% of your overall production time. So looking at other benefits of automated inspection, we did talk about the reducing the cycle time or improving production rate. We mentioned that you're not going to completely eliminate your inspection time, but even if you decrease that by 50% using an automated system or a semi-automated system, you're able to save 15 to 20%. And the reason I say you're not going to completely get rid of your inspection time is, you may have something come up that's flagged or questionable and have to have the inspector go in and take a look at it. There may be things that you can't quite get out of the inspection system as it stands, but any improvement would be great. Of course, if you reduce cycle time, most of the time you're going to reduce labor costs, but I pointed out a couple here because they're even more relevant. The inspection time, of course, if you're not performing an individual ply inspection over the entire ply, over the entire part, you're going to reduce the time that's required for the operator to do that. And associated reporting will also be decreased because you should be able to have your automated system perform those reports and maybe have sign-off or verification required by the operator inspector. The other thing that there is a potential for is the ability to run multiple machines with a single operator. So instead of one operator sitting to watch a single machine perform inspection, you may be able to get away with an operator where where there's not maintenance going on. He may be able to run 2 or more machines. Of course, you'd have to schedule in maintenance and inspection to go along with that, but it does give that option in the future. The other thing that I want to point out, for aerospace type parts especially, there's stringent quality system requirements associated with them. And an automated inspection system has the potential to improve, the accountability for that as well. So, performing manual inspection, of course, there's always potential for not catching a flaw, or maybe reporting something that's not there, or even as you're reporting, making a mistake on the report. So you do have the potential for fewer quality escapes, I call them, or mistakes in that reporting. The other thing that it does is it can perform and keep a permanent digital record of a part. So, as you're laying up a given part, you could track over 6 months, a year, 10 years, whatever it may be, how well that part lays up. And you can use this information to help, determine when maintenance may be required on the machine, whether you may want to look at, redesign a part slightly to help it, in manufacturing. So if you're always dropping toes in a single location every time you build a part, you could take that data design and see if there's something that can be done to improve that to help you out. So, there's quite a few advantages, but why haven't we got to a point where we have an automated inspection system? Well, frankly, it's pretty difficult. There's been quite a bit of work done. We're going to talk about some of that work, not all of it, but some of it in the next few slides here. But you do have many differences in your part, whether it be your actual part layup, the size of it, the tooling associated with it, some of your environmental conditions. Another one to think about is analysis time. So you can have this great scanning system. It collects a lot of data, especially on some of these large parts shown. But if you have to analyze that and perform, your checks to see if you conform or not conform, and stop the machine before you lay that up, of course, over top of that, you need to make sure you're analyzing that with enough time to be able to stop the machine without slowing it down for production. And then the other one is results interpretation. So, how do you interpret results if you're looking at point clouds? What's one point versus the other point? Is something FOD, is it not FOD? How do you actually make that determination on the fly? So taking a look at kind of the fully manual inspection that you saw the pictures of in the previous slide, and what hopefully we'll get to an fully automated inspection system, I wanted to actually show an example of what I'm going to call an assisted manual inspection. One example of that, which is actually developed by Electro Impact, and that is an integrated laser projection system. So what that is actually you have a laser projector that is integrated into the machine reference system. So you're able to actually project data, your laser files, onto a part with that machine reference system. So as you're moving the part or as you're moving the machine, you're able to actually get updates of where those features are live and real time with that established system. You have the potential for multiple lasers on a single part. So if you have a large part, you're not relying on one laser to actually perform that projection along that same system. You can have multiple set up along, whether it be an x-axis, rail, or permanent locations mounted throughout the cell. Looking at that a little bit closer, what you're able to do is you can check for features on a given layup. So you could start looking at fiber angles, program laps and gaps, ply coverage. You could take a look at when there's a defect, where that toe or course was supposed to be laid up, how far it was supposed to be laid up, and what may have went wrong along the way. So you start with the validated process. You can actually, in VCP, so again, Vericut Composite Programming, you can actually export both the NC data that you run the machine with and the laser projection data to that same reference system. So everything right from the beginning is established with the same reference system going to the machine. From the machine, you can use the operator panel to select what portions or what features you may want to display on the part, and use the laser projector to actually project those boundaries or features for verification onto the laminate. So that was just a quick overview of, again, an assisted manual inspection process, the integrated laser projector. Now I'm going to spend a few minutes just talking about some potential automated inspection techniques that we see may be useful for the future. And when we talk about automated inspection, there's really a few different types of inspection you could think about during composite manufacturing. You could have in situ or post layup and cure. Really, where we see the greatest advantages in the in situ inspection, because you're able to actually monitor that material as it's either incoming into the head or to the machine, and start looking for twists, breaks, splices, verifying width tolerances, and also looking for FOD on the material before it's laid on the part. And what you could do with that is, before it's laid on the part, if you see that there's an error, you could stop the machine, notify the operator that there's an issue, and either have that laid onto a scrap table somewhere, or have the operator, make the proper adjustments before it's laid on the part. The disadvantage that I'd say with inspecting the incoming material, though, is you're not verifying that you're laying up material where it's supposed to go. So just because you don't have some of these features in your material doesn't mean you're going to lay up material within whatever your tolerance may be, maybe a plus or minus 1/8 of an inch or plus or minus 1/4 inch of the intended ply boundary. The other in situ inspection would be place material, I'll call it. So, right after you lay material, go ahead and inspect that with either a system that's on the head or, a standalone unit that may be on the back side of the part or in another location. And with that, you'd be looking for twists, breaks, splices, width and end tolerances, and placement tolerances. FOD, and I make a note on the FOD here, or foreign object material, so anything that's not supposed to be in the part being there. So I mentioned FOD here because you do have a bit of a challenge when you are inspecting the laid material to look for FOD underneath the part. So you could look at the thickness of the material, and if there's an abrupt change in thickness, you may assume that that's going to be FOD, but you do have much more difficult time finding that after you lay over the top of it. And then post layup and cure, again, the big thing here is that you're not going to typically be able to do much with your part if you find errors at this point, because you're already fully covered. So if you find that there's FOD a quarter of the way through the part, there's not much you're going to do with it other than report that it's there and determine whether or not it's going to be an issue for that specific part. Just quickly looking at some of the techniques, and this isn't all-inclusive, but just pointing out a couple. For those in situ inspections, you could have laser-based systems, vision-based systems, forward-looking infrared systems, or hybrid systems, which could be a combination of any or all of the above or others. And then post-layup, again, talked about it's not extremely important for what we're talking about here, but that would be ultrasound or CMM, some type of X-ray technology, CT, for instance, or or thermography. So looking at a couple of systems that are, currently available, I'd say, is Ingersoll has a real-time inspection system, which actually takes a look at that incoming material as we talked about, and inspects for twists, breaks, splices, toes out of tolerances, and it notifies the operator and records locations of defects or prevents those from being laid up on the part. Then MTORAS also has a similar type system, which uses a laser inspection system to detect defects in incoming tape to its ATL machines, and if there are defects associated with that tape, it'll actually lay those up on a scrap table and avoids laying them up on a tape on the actual part. One additional system that I might go into was actually work being done with Flightware and Dave Mass and CGTech helping out with that. And that's actually using a line scanner. And what it's doing, we'll talk about it a little bit more on the next couple slides, but after the part's being laid up, it's actually going through and scanning with robotic off-the-shelf system and doing feature recognition to determine whether or not individual features are where they're expected to be or not. So again, it's really taking a look at how do we go from the layup of the material to the inspection and make that an automated process where we can determine whether or not those features are in the correct locations. And this was the other video that I was going to show, but I thought I'd show the picture since videos typically don't work too well in these presentations. And what I was showing was a commercially available system that was actually performing that laser scan, as we had mentioned, with a robot over top of the laminate. And that was providing a point cloud to a system that was actually determining where features are located on a part. So when we talk about features, we're really looking at where edges of toes, where the feeds, the cuts, and splices may occur. And then actually feed that data into a location analysis software within VCP or CGTech's Vericut composite programming solution to determine whether or not they're actually where they're expected to be. And what you're able to do is actually change your tolerances to make sure you're within tolerance or not within tolerances and flag that to the user. And right now this was done with a system not on the layup head, but the next step to this would be to take this and add it to the layup head and perform the inspection in situ. This just showing that example again, where you take a look at where these features, the edges or end placement may be out of spec, and report those back to the user at the time. So with that, I am just about done with the presentation. Again, wanted to just pull this slide up again, just to hit on the point again that there is significant improvement that can be done for automated composite manufacturing, and what I would say the low-hanging fruit in both these cases would be the inspection process. And with that, I would like to thank a number of individuals, Dave Mass from Flightware, Electro-Impact, CGTech, and then Jeff Sloan and Taylor for helping put on this webinar. And with that, I think we are good to go ahead and open up the floor for questions if you're available, Jeff.
I am. Thank you, Matt. Appreciate it. We do have a few questions coming in, so why don't we just go ahead and jump right to those.
Okay.
The first one is this. Can you use automated fiber placement to create geometries with various angles, for instance, a part with 0, 90, 0 step with radius in the corners?
Could you repeat that question again? I thought I knew where you were going, but I just want to make sure I understand the question before I go ahead and try and answer that.
Yeah, can you use automated fiber placement to create geometries at various angles? For instance, a part with 0, 90, 0 step with radius in the corners.
So if I understand the question correctly, it is, can you use fiber placement for differing angles? And I'm not sure if that's referring to the tool or the actual layup, but I'll answer both. So you have the flexibility with fiber placement to lay almost any given ply angles or fiber angles or orientation that you want to. So you could lay 090, 0 or 0 45, minus 45, 90, 90, minus 45, 0. You have that flexibility. You also have the flexibility to lay up on curved tools. You do have limitations, though, on how much curve there is associated with that tool. So if you could imagine trying to lay up a right angle, for instance, so you're not going to get compaction because you require compaction to help lay these or place these toes. So you're not going to necessarily get compaction in that corner, so it would cause bridging and potential defects going through. So you do have limitations on what that tooling would have to be.
Okay, great, thanks. Next question is this. What types of technologies are being developed in the specific area where we have very complex shapes but not complex stacks?
So I guess I don't fully understand that question as well. I apologize. So complex shapes and not complex stacks. So I guess one of the things, if they're talking about manufacturing processes, one of the things that you could do is, there are tape laying, and we talked about using tape laying for flat charges. So if it's not a complex shape, you could use your tape layup machine to get charges and actually cut those out with an integrated ultrasonic knife, and from there post-form those charges to whatever shape you need. So it would be a hybrid system such as that. If you're talking about inspection systems, you would still be able to use line scanners or some of the hybrid systems for performing those inspections on complex parts. In fact, I would think an automated system may be more advantageous for those complex parts because it may be hard to determine what's conforming and not conforming.
Okay, great. Next question is this. How is a ply drop-off treated? Is it treated as an FOD or FOD?
Ply drop-off, so it depends if that's intentional or not. So if you are intending to end up ply at a given location, obviously that's expected. So that's defined by your ply boundary. If you have a toe that abruptly drops off in the middle of a ply, unexpectedly, I wouldn't necessarily consider that a FOD unless it's removed before repairing. Typically, that's from a broken toe or a toe failure. So if you didn't remove that toe and replace it, then obviously it would either be FOD or a non-conforming, short toe in that laminate at that point.
Okay, good. Next question is this. Can the laser or vision system handle the AFP vibration? How does vibration inspection?
Yeah, so that's one of the questions. So the laser projector, it does work well. Vibrations obviously can be an issue, but it hasn't been too much of an issue in the past. The laser, that's still to be determined how to get it to that point. So hopefully we come back in a little bit of time and have a better answer to that, but not quite sure at this point.
All right, next question is this. Is there a method to inspect or verify orientation and fiber direction for a placed material during layup?
So currently I do not believe that is the case. So that would be one of the advantages of looking at an automated inspection process. So you could start taking a look at, whether you have a projection over that path and verifying that projection at the same time, or you have the ability to actually measure the toe edges and compare that back against what was expected through your actual part to verify that your ply orientation is what it's supposed to be. And of course that gets to be even more challenging as you look at more and more complex parts with contoured shape, because you start steering those toes and you have to verify that where those toes are steered, they're not steering too much or too little, actually following the intended path. So you have to verify that against your nominal layup.
All right, next question is this. You mentioned various inspection technologies such as laser scanner, FLIR, etc. that can be used. Can these technologies actually detect every single defect, and especially at the tolerances required? For aerospace parts in particular, tolerances on gaps and overlaps can be very tight.
Yes, so that's where I'm not going to say every feature can be detected, because as soon as you say every feature can be detected, someone comes with a requirement that that may be more challenging to it. For many of the standard detection requirements, do see that these systems, whether it's one of them individually or a combination of the units, you would be able to get what you need. Now, of course, if you're looking at trying to have tolerances on, I don't know, the micron level, it might be more challenging, but for standard inspection, I'd say yes.
Okay, next question is this. Can you explain more what you mean by COTS in your presentation? COTS.
Commercially off-the-shelf system. I apologize for that. I should have explained that. So it's readily available system. You can actually purchase that as is. What it does not have, though, is that feature recognition and comparison tool built into it. So it would have the laser scanner that you could actually hook up to the robotic system.
Okay, next question is this. How well do these inspection technologies work if you have two plies on top of each other that have the same orientation?
Yeah, so what you have to start looking at there is then your depth of those materials, because you're going to have an offset, whether it's, typically these are a few mils, so you have to make sure you have the resolution to determine the actual thickness of that laminate at a given location. So you can use that to determine overlaps or gaps, or if there's a toe missing where it's supposed to be, splices, that sort of thing.
All right, next question is this one. What is the accuracy tolerance of the laser projection system? Is it currently being used in production for ply boundary inspection?
So the tolerance, I believe it's actually at 1/1000th of an inch over 10 foot, and it is being used in production in systems currently.
Great. Next question is this. What is the biggest challenge before automated inspection can be fully achieved?
Biggest challenge before automated inspection can be achieved. Boy, that's a tough one. I don't know what I would consider the biggest. I would have to think about that one for a little bit. I talked about many of the challenges, but I don't know what I would consider the biggest at this point. I think, maybe it's how to deal with the large data and analysis, and the analysis time associated with each of those courses that you're inspecting, especially if you're looking at a part where you may lay up one course and immediately following that lay up a course right over top of that. So you need to be able to figure out over it maybe a several meter length course. Do you have any defects in that within a couple of seconds, and how do you do that? What do you do with the data, and how do you store that? So maybe data handling and analysis, I guess I would say.
Okay, good. Next question is this. What is viewed as an acceptable false positive rate for automated inspection? What is an acceptable missed defect rate?
To me, that's going to be determined by the end user. It's really dependent on the part you're looking at. You know, typically for these quality systems, especially for aerospace quality systems, you do have very stringent requirements. So if you're relying on the automated system as your sole source of inspection, you need to be nearly perfect. Otherwise, you know, you're talking about the escape if there is something out of spec. So you have to make sure you're at least meeting that spec, and that could be different for each part. You know, some parts you may get 10% of toes out of tolerance, whether that be end placement or overlap gap. Some you may not have any. So so yeah, that's dependent on the part, but you need to be pretty much perfect.
Okay, looks like we have one more question. For a C-scan of a plate of composite nanofiber, especially with UT phase array, what do you recommend?
So I would say that is not my expertise at all, so I would not want to recommend anything at this point on that. I don't know. You know, I could probably point that person in the right direction if they want to contact me, but I would hate to give recommendations on CT and ultrasound scans for that.
Okay. Here's one more question just came in. Can you disclose who is currently using the laser projection system for ply boundary inspection in a production environment?
I don't believe that I can disclose that. If they want to follow up with an email, I will verify whether or not I can get that out to them. I do know several people that are, though, so I can verify whether or not I can release one or multiples of that.
Okay, and also just so our attendees know, all these questions are being saved so that there can be follow-up afterward.
Okay.
Right. I think that brings us to the end of our questions. Again, I want to thank all of our attendees for participating today and for sitting in. And Matt, I want to thank you for presenting and answering questions. I appreciate it.
Thank you. I appreciate it, Jeff.
All right, everyone, have a good day, and we'll see you next time Composites World has a webinar. Thanks a lot. Have a good day.
Thanks, Jeff.